pleasure to be here. I always like to come to the TGI. So, in my lectures, I will discuss the application of field theory techniques, so in particular bosonization and synchronization methods, to, let's say, quantum spin chains, so models of magnetism in one dimension. And throughout this series of lectures, I hope you'll ask lots of questions, you will interrupt me. So I prepared some material. If all of you know this already, this is very difficult for me to judge what you know, what you don't know. So just tell me, or if you're shy, don't tell me. Tell my students who are here, Bruno and Thomas. Yeah. And then let me know, and then we basically can move on. So I thought I would start today by just creating some context. So I will talk about these quantum spin chains and field theory descriptions of these quantum spin chains. But of course, before doing that, I should tell you why this is an interesting area, why people are studying this even now, and what the interesting questions are. And in order to do that, I should start talking a little bit about magnetism in the first place. All right, so first lecture now will be essentially some background. On models of magnetism. Okay? And the first question to ask always is, does the Hamiltonian have a form? And the Hamiltonian indeed has a form, so the typical Hamiltonian, typical model we write to describe magnets is a Heisenberg model on some lattice, which is appropriately chosen. And the lattice is essentially specified once you specify all the links between spins, and these spins interact by what's called a Heisenberg exchange interaction, which is some interaction of these forms, and of this form, and these would be quantum spin operators. Okay, so I have a d-dimensional lattice. And let's say jk run over nearest neighbors. So that would be a typical model. And I should say, so these are quantum spin operators, so there are three of them, Sx, Sy, Sz, at every side of the lattice, and they fulfill this angular momentum algebra as alpha, j, as beta, k. So these would be spin operators side j, this would be spin operators side k, and this would be I, epsilon, alpha, beta, gamma, s, j, gamma, if j is equal to k. Yeah, so this basically just expresses that, the fact that at every side you have an angular momentum. Yeah? And the size of the angular momentum depends on the problem you want to study. Yeah, so it could be spin a half, spin 1, spin 3.5, spin 2. So all of these exist in various materials. Okay, so in general, so we are interested in a spin S representation at each side. Yeah? And the first question, of course, is, well, okay, so the Hamiltonian has a form, but why does it have this form? Where does it come from? And I'll show you that later today. Yeah, so for the time being, I want to say is, well, let's just take this Hamiltonian. Many of you will have seen this before. Anyway, and let's talk a little bit about the physics that comes out of models of magnetism specified by such Hamiltonians. Now, the first thing to notice is, Okay, so this is not a free theory. Yeah. It's not, this is not a model of free bosons or free fermions. Yeah, so it's not a free theory, so it's given entirely in terms of these angular momenta. There are many of them. And what's even worse, there's no small parameter. Yeah, so this generically is a very, very hard problem. Okay, and so there is no general solution to models of magnetism. Okay, so in general, very hard problem. Which remains unsolved. Okay? However, there are some circumstances in which, although the Hamiltonian doesn't have a small parameter is generated dynamically, so through the physics. Okay? And that allows us to describe certain regimes of the physics of these magnets in a simple way. Okay, so, however, in 3 dimensions, yeah, at low temperatures, or in 2 dimensions at temperature 0, what happens is that the continuous symmetry that underlies this Hamiltonian is spontaneously broken. So what happens is that the SU2 symmetry of H is broken spontaneously. So what it means, so first of all, this SU2 symmetry simply means the Hamiltonian commutes with the global spin operators. So J equals, so I sum over all sides, and here I have as alpha J. So this commutator is equal to 0. Yeah. And it's kind of obvious because in the Hamiltonian all SU2 indices are contracted, so you would expect this to be true. Right? Okay, so the Hamiltonian has this spin rotational symmetry, and that basically means there's no preferred direction in spin space, yeah, which is clear from the form of the interaction. But what happens is at low temperatures, this continuous symmetry gets broken spontaneously, so the ground state, or the density matrix at low temperatures selects the preferred direction. Okay? And it is this spontaneous symmetry breaking which gives rise to a small parameter, which allows you then to solve the low temperature physics of this model. So let's see what we mean by that. Okay, so spontaneous symmetry breaking means now we pick up an anomalous expectation value, and so 1 divided by the partition function trace e to the minus h over kBt. So that's the thermal expectation value of SZJ. Now becomes m, some order parameter, e to the I vector pi dot rj. This becomes different from 0. And so pi, so I consider now just a 3-dimensional cubic lattice. Yeah? I should write this in a moment. So is this 3-dimensional vector pi over a naught. A naught is a lattice spacing. Times 1, 1, 1. And z is the partition function, so trace e to the minus beta h, e to the h over kBt. Okay. And so basically what it means is if you have your three-dimensional crystal, if you go from one side to the next, the direction of the expectation value of the spin changes sign. So you basically get a configuration which looks like this. Yeah? So this is the long-range order. So this has the pattern of magnetic order that emerges if this symmetry is spontaneously broken. And this is what you see actually typically in most magnets. Yeah? It's not ferromagnetism that emerges naturally, it's actually this anti-ferromagnetism. We'll see why. Okay, so now this is spontaneous symmetry breaking. And as I said, once this has happened, now you have this order parameter here. Okay? And once you have this order parameter, so that generates now a small parameter. So what is the small parameter? The small parameter actually are the fluctuations around this ordered state. Yeah? So the way to think about this is these spins are not exactly frozen, they fluctuate a little bit. Yeah? But if this ordered moment here is large, so the maximum value, so just to make sure that there's somebody who's paying attention, so what is the maximum value n can take? S. Okay, because I said I have a spin S at every side. Okay, so the maximum value you can take is S. And if this order parameter is close to the maximum value, so it's not equal to the maximum value, but it's close to it, then you have a small parameter, which is roughly speaking S minus M. Alright? And then fluctuations typically will be small, and you can describe them by doing an expansion in this emergent small parameter. And you can do this in many ways. So one way of doing it is to write a Landau-Ginzburg theory, order parameter theory. So just to write some for some vectorial order parameter, some lambda phi to the 4 type theory is one way of doing it. That's not typically what's done in this in the literature for magnets. So what is done there is something which is completely equivalent, and I'll very briefly discuss this. So if you're interested now in describing the physics of the ordered phase, first of all, what is the physics of the ordered phase? Just to see whether somebody has covered this material already. I'm not asking Pasquale. So spontaneous symmetry breaking. What happens when you spontaneously break a symmetry? Yeah, so you get Goldstone modes. I mean, so essentially, when you spontaneously break a continuous symmetry, you must get excitations which don't have a gap, which start at zero energy. Yeah, and typically you will have a linear dispersion, some kind of critical modes. And the number of these modes is related to how you have broken the symmetry. Yeah? This has to emerge here. And that physics, the physics of this Goldstone modes, the physics of order, you can solve very easily. So let me just tell you one way of doing this, which is the standard way this is done in the literature on magnetism. So essentially, for this Néel-ordered state I've just described here, so what you do is, okay, so the classical ground state is just the Néel state, which is the pattern I had described before I had to erase it. And now what you do is, now step 1 is you rotate the spin quantization axis in such a way, in such a way that the Néel state maps onto a ferromagnet. So what I mean by that, so the nail state was this pattern, up, down, up, down, down, up, down, up. And now what you do is, on this side, you keep the quantization axis in spin space along the z direction. On this side, you rotate it by 180 degrees. Yeah? So that the quantization axis actually goes down, goes up, goes down. Yeah? So you just, for each of these spins, you choose quantization axis according to which sublattice it is on. Yeah, so so essentially this state can be described by looking at two sublattices. Okay, there's no color. So there's this sublattice, all spins up. Yeah, call that A, and the other ones, all the spins are down. You call B. And essentially what you do is you rotate the quantization axis on all the B spins by 180 degrees, yeah, and define new spin operators, and the transformation simply is S tilde x, j, tilde yj, tilde zj is minus S tilde, Sxj minus Szj Syj if J is on the down sublattice, say. Okay? Once you have done that, this classical ground state, so this pattern, this ordering pattern, corresponds to a ferromagnet, all the states pointing in the same direction. That's what we wanted, because now what you do is you use what's called this Holstein-Primakov transformation. Okay, so you do this, then step 2. Okay, so first of all, the Hamiltonian in the new spin operators now becomes minus j Szj Szk. And then here we have plus a half S plus S plus plus S minus S minus, where S plus minus is xj plus minus I Syj. Okay, so this basically used to be just S plus S minus plus S minus S plus. Yeah, now because we have rotated on one of the sublattices, you see you break now explicitly S22 symmetry. Yeah, which is clear because your ground state actually broke it. In the form of this Hamiltonian. And then step 3. So you use this Holstein-Primakov transformation. Which is the following: S Z J tilde is just S minus A delta J A J, and S tilde plus J is equal square root to S minus A delta J A J, where these A's are actually canonical bosonic creation annihilation operators. Yeah? So this, you should check. I mean, if you have never seen this before, you certainly should convince yourself. This transformation, yeah, where these A's and A daggers fulfill the usual boson commutation relations, reproduce the SU2 commutation relations. Yeah? So if you just use this, with these commutation relations, the S tildes will fulfill this angular momentum algebra you have. So this is a faithful representation as far as the commutation relations are concerned. Yeah. There's of course a problem associated with it, and the problem is that the Hilbert spaces are not the same, because the Hilbert space for the spin operators is finite dimensional. Yeah, it would be 2s plus 1 states, whereas the Hilbert space associated with the bosons is infinite dimensional. So what you really should do is you should supplement this with a constraint, which is that the number of bosons has to be less than 2s. Because then you see, this, looking at this identity here, the Hilbert spaces would be the same. So there's really a constraint. However, at low temperatures, you can actually drop the constraint. And the reason is, and that's also why we did this rotation of quantization axis. Okay, so at low temperatures, the density of bosons will be very small. Yeah, so that's the smallest of these fluctuations. So essentially, the part of the Hilbert space that the model explores will be very close to where in the rotated coordinate system all spins point in the same direction. But there, you're very far away from running into the other end of the multiplet of spins, and there you don't have to worry about the Hilbert spaces being different. Yeah? So now what you do is you substitute this back into the form of the Hamiltonian, this one here, and now you do an expansion, which usually you just do to quadratic order in the first instance. That gives you a free theory, which you can solve exactly. And that free theory will have coherent single particle excitations, which are the Goldstone modes. Exactly the right number. So that physics you get very easily. Then, once you do this expansion, of course, you also get interaction terms, and those you would treat in perturbation theory. And once again, so formally there's no small parameter. So in order to get a formal small parameter, what people often say is, well, it's assume S to be large, and then do a 1 over S expansion, which is what this would be. But you don't have to do that, because the series you get, if you calculate physical quantities, are asymptotic series. And they're very good even if S is a half. Yeah? And the reason, once again, is you describe the small fluctuations around the ordered moment, so it's really the physics which gives you a small parameter, yeah? Not the largeness of the spin. So this is, in a nutshell, the standard treatment of magnetisms in 3 dimensions, or in 2 dimensions at 0 temperature. So there's always long-range order, which is also typically what you see in experimental magnets, and the dominant features there is the long-range order and the fluctuations around the long-range order and the Goldstone modes which carry the dynamics. Yeah? So this is the kind of standard model of magnetism, if you wish. And so the physics of this ordered phase you can understand by these very elementary means, quite simply. All right. And I gave you this background in order to contrast this with what happens in 2 dimensions at finite temperature, or in 1 dimension at any temperature, even at 0 temperature. Because there, the big difference is there is no long-range order. So in 1 dimension, so this Heisenberg model, there's a theorem, the Merrill-Wagner theorem. It tells you it cannot break the SO2 symmetry spontaneously. Okay? So which means this whole premise we have done here, expand around some ordered state, doesn't work. And therefore the physics in the 1-dimensional context is very different to what you see here. There are no Goldstone modes, there's no long-range order. This is replaced by something other, and the other is actually quite interesting. Yeah? And so that's the reason why lots of people are interested in quantum spin chains. So let me give you a short list of what's interesting about these spin chains. Do you have any questions actually about this background material? Now is a good time to ask. No? So you don't ask because you knew all that, or you ask because you didn't know it and you didn't learn anything now in the last half hour. All right.
The sign of J was immaterial.
The sign of J, I had chosen the antiferromagnetic sign, so for me J was positive. And that gave you this standard ordering pattern, which I call the nail state. If I had chosen the other sign, the ordering pattern would be different because all the spins want to point in the same direction, so that would describe a ferromagnet. But once again, you would have spontaneous symmetry breaking, and there would be Goldstone modes, but the precise nature of the Goldstone modes would be a little bit different. Because for the ferromagnet, Goldstone modes actually have quadratic dispersion, whereas for the antiferromagnet, they have linear dispersion. But roughly speaking, the procedure you use to solve it would be the same. All right. Okay. Now let's talk about these quantum spin chains. So. And ladders. Okay. As I said, so the situation in one dimension is fundamentally different because you cannot break this SU2 symmetry spontaneously. So there is no magnetic long-range order. Okay, and what happens instead is what's called quasi-long-range order. And that means if you look, now let's go to zero temperature, to the extreme limit. If you look now at the one-point function for Sz, so there would be no long-range order, so this would have to be 0. But if you look at the two-point function, what you see, this two-point function decays like the distance between your two spin operators to some power. Yeah, so there's a power law behavior when the distance is large. And that basically now means this is the closest you can come to long-range order. Long-range order means a spin at one end of the sample is perfectly correlated with a spin at the other end of the sample because of the long-range order. So in one thing it cannot happen, because quantum fluctuations are too strong, so it always melts this order. But what you can have is that spins which are very far away from each other are still quite strongly correlated. And the strongest you can have is essentially a power law. And so this, for some of you might already start to set some bells ringing. So this power law behavior in one-dimensional systems, you should be able to describe by some field theory, which in this case will be some particular conformal field theory, and that's where we'll be going. Okay, so what this means is the correlation length formally is infinite. And then, as you know, from Professor Fusano's lectures, if not before, so if the correlation length is infinite, then you are at the point of a phase transition. Okay? And so here, this phase transition would happen at zero temperature, does happen at zero temperature, and this is known as a quantum phase transition, or quantum critical behavior. And so it's very anomalous. So you have it now at zero temperature, so it's a ground state property. And you can see this experimentally. So this is one of the interesting things that happens in low dimensions. And so this is typically described by conformal field theories. Okay, so other things that happen in one-dimensional systems, Goldstone modes are really very boring. I mean, so it's very simple, because their quantum numbers are the naive quantum numbers. So in terms of the spins, these Goldstone modes, they would just carry the quantum numbers of a spin thing. It would be a single particle excitation. What happens in the one-dimensional system is you have typically something which is called quantum number fractionalization. quantum number fractionalization. And so what I mean by that is, now consider a spin a half. Spin a half has two states, up or down. Yeah? And now consider a spin chain where you have this spin a half. So consider something like this. Now, still, if you flip an individual spin, yeah, you basically change the global quantum number by 1, as said by 1, because instead of 1 up, you have 1 down. Okay? And so a spin flip typically carries spin 1. And these Boltzmann modes, they would carry delta Sz equals 1. Now what happens, and we will see this in these quantum spin chains, the elementary excitations actually don't carry spin 1, they carry spin a half. Yeah, which in the first instance sounds crazy, because your elementary excitation that you naively would have on the basis of the individual constituents would tell you you cannot make an excitation which is doesn't have an integer spin, yeah, but you can. Right? And so this is an example of quantum number fractionalization. Other examples would be electronic excitations. If you have models of electrons, typically don't exist in one dimension. Yeah? So there's no stable electron excitation. It falls apart into a piece which only carries spin a half and another part which carries a charge. And this is very generic in this 1D systems, and that's of course interesting. And it's something that needs to be understood. So quantum number fractionalization is zero temperature critical points. And then another thing you can study is confinement. Yeah? So in some models of magnetism, variants of the Ising model that I will describe later, you will have some elementary excitations, which carry a particular quantum number, but now what can happen is that they are confined in the sense that quarks are confined, yeah? Which means if you try to separate them, it costs an energy which goes with the distance. And so here in this one-dimensional context, it gives you models which are essentially exactly solvable. You can solve more or less exactly, which show this phenomenon which you can then study in some detail. So there's lots of interesting physics, some of which I've mentioned here, which is why we want to study, or many people want to study, these quantum spin chains. Okay, and that's where we want to go. Now, a particularly nice feature about magnets in general, and low-dimensional magnets in particular, is there are lots of experiments which actually measure all the things that you might calculate here. It's not very expensive. You don't need to spend 10 billion to do an experiment on a quantum spin chain. So there are lots of experiments. They measure a variety of properties. They measure, in particular, of course, thermodynamic properties. That's a standard measurement, but they give you, through spectroscopic measurements, through scattering measurements, very, very detailed information about the dynamics of the system. And I should briefly just say what these experiments are and what they measure. So what are the main observables we'll be interested in. So the best experiment, or some very, very nice experiments, are neutron scattering experiments. And what you do there is, here you have some sample, which should be a very large crystal of the magnet that you want to investigate. It should be a single crystal, and the larger the better. So then what you do is, you prepare a beam of neutrons and a particular energy and a particular momentum. Yeah? And these neutrons, they carry angular momentum, so you scatter them off the sample. And then what you do is you put a detector somewhere, And here you measure the number of neutrons with a different energy, and the energy you can tune. They can choose which energy they want to measure, and a particular momentum. So you should think about this in three-dimensional space, and they have detector banks all around, yeah, which basically tunes this. Okay, and what happens in an experiment like this, you have an energy transfer. Omega is E minus E prime, and a momentum transfer, which I call Q, which is P minus P prime from the neutrons to the sample. Yeah? And then also, okay, and this energy and momentum has to go somewhere. Yeah? So where does it go? It goes in making excitations in the crystal, in your sample. So by doing this, in a sense, you measure properties of excitations in the sample. Yeah? Because you pump some energy, some momentum into the sample, and that has to go into propagating modes in your sample. So now, you can work out more precisely what is actually measured here. So what is measured is they count the number of neutrons, so they measure a cross-section, and this inelastic neutron scattering cross-section is proportional to a particular correlation function of your spins in the sample. Okay, and what it is, so it's delta alpha beta minus Q alpha Q beta divided by Q dot Q. And so integral 0 to infinity dt e to the I omega t 1 over L sum L e to the minus IQ dot Rj minus RL. Rj and RL are positions or spins in the crystal. And here now we have 1 over Z trace e to the minus h over kBt. S alpha j t s beta L observed. So that is the expression in its full glory. So that's called okay. So this piece here is called the dynamical structure factor. So that's really what they measure. Okay, and then that's what you have to calculate. Now, from a theorist point of view, because I take you're a theorist anyway, so what you have to calculate, the difficult piece, is to calculate this correlation function. So that's a finite temperature, or even at zero temperature, it's interesting. If the temperature is low, to first approximation, forget about temperature effects. So that's a particular retarded two-point function of spins. So the task is to calculate this object. Right? Then you can compare the experiment. There's some Fourier transform. And so one of the things we'll do is, and what these field theory techniques I'll introduce you to are useful for, is to essentially calculate this quantity here in some field theory limit. Now, once you have this, you might say, well, all right, so this is kind of very indirect information because it's a particular correlation function, you know, so what do I really learn by looking at something like this? Well, if you look at this dynamic structure factor itself, so this is called S alpha beta of omega and Q. It has a lot of information about the spectrum of your Hamiltonian. And by looking at this correlation function, once you develop a little bit of experience with this, you can immediately basically make some statements about what excitations are like in your magnet. So the reason is, just look at a diagonal component. Yeah, so this is a matrix, so these are spin indices, alpha and beta, so x, y, and z. But now let's just say we have SU2 invariant theory, so spin rotation invariant theory, so then essentially you just need the diagonal ones. Let me just look at the diagonal ones. Okay, and okay, so now it's this correlation function. So now let me look at this correlation function at zero temperature, for simplicity, in a spectral representation. Yeah, so take the temperature to be zero, and spectral representation in terms of eigenstates of the Hamiltonian. So this is the Hamiltonian, this would be the eigenstates. Okay. So essentially what you do at zero temperature, this part just becomes ground state as alpha j of t as beta L of 0. And now all you do is you essentially insert a complete set of states between the two spin operators. It's called Lehmann representation. So then this becomes a sum over all eigenstates. Here you have ground state S alpha j n absolute value squared. Then you can just do the Fourier transforms. They just give you some delta functions. Omega minus En minus E ground state delta to the D Q minus Pn. Yeah, so that's the Lehmann representation. So question, yeah, why do you have these delta functions? The physical principle. Yeah, okay, so Martin is the only one who kind of answers question. Yeah, so it's energy momentum conservation. Yeah, because this is the energy you pump into the system, and it has to go in making an excitation from the ground state to one of the excited states, because energy can't get lost, and this is the same for the momentum, and using that the ground state momentum is equal to 0. So now you see. Okay, so this correlation function, if I look at this spectral representation, you have some matrix elements here. Yeah? But then these delta functions, they would follow the dispersion relations of elementary excitations. So in particular, if you have a Goldstone mode, then this S alpha alpha of omega q would be proportional to a delta function omega minus epsilon of q, where epsilon would be the dispersion of your Goldstone mode. And this basically, you can work out what these matrix elements are. So this is the result of the calculation. And this generalizes, so typically if you have coherent, so coherent means so infinite lifetime, elementary excitations with spin quantum number 1, you always get a delta function. Yeah? So Goldstone modes is one of these. That's not what will happen in the one-dimensional context, because once again having to do with this quantum number fractionalization, so rather than having a sharp line following the dispersion, you will have what's called a scattering continuum, which comes from the fact that elementary excitations carry spin 1/2. And to make something with spin 1, you need 2 of them at least. So there's quite a lot of information in this particular correlation function, and it tells you a lot about the phenomenology of the excitation spectrum. Okay, and so typically this is the most important example for these magnets, the dynamic structure factor, but more generally, most spectroscopic measurements will measure some 2-point function, some retarded 2-point function. Yeah? And that's what you want to calculate. All right, so then the last thing I should say in this introduction to magnets is, okay, so we'll be talking about one-dimensional modules, yeah, quantum spin chains. Is this reasonable? Because any crystal is three-dimensional. Yeah? So what the hell am I talking about? Okay, so in order for this to make any sense, there has to be some regime, yeah, in which the three-dimensional effects are small. Yeah? So what is that regime? So typically, these materials, which are described by as quantum spin chains, have the following structure. So it will be a crystal, three-dimensional crystal, and let's say we have the spins in the crystal, and the spins predominantly interact along one direction. So here are the spins, and then you have this exchange interaction between spins, which is very strong along these directions. Okay, and so then a zeroth order approximation would be, okay, they also interact, of course, in the perpendicular direction by some exchange, which is much less. And so typical, so J perp over J is, let's say, 10 to the minus 2 or something like that. That would be a good one-dimensional realization. So now, the zeroth order approximation would say, well, just forget about this coupling altogether. Yeah, so then you have an ensemble of uncoupled chains, and then you literally can work with these one-dimensional models. Okay? But that, of course, now neglects the effects of this interchain coupling, and the obvious question is this reasonable? Or in what regime is it reasonable? Now, the regime in which it is reasonable is a little bit counterintuitive at the first instance. So now we have this scale, this energy scale, which I call omega, at which we probe our system. So for example, in this neutron scattering experiment, it's the energy we pump into the system. Okay? Or if you do some thermal measurement, your scale would be the temperature at which you do your measurement. Okay, so now if omega is comparable to J perp, to this energy scale, you cannot neglect the fact that you're three-dimensional. Okay, so you have to be in this window to see the one-dimensional physics. So if the scale at which you probe the system is much larger than this coupling, you can take it into account in perturbation theory. And so it will change your answer, but only in a very small way. Okay? And in particular, we will be interested in this regime, where the frequency is also small compared to the strong exchange, because here we can take a field theory limit. So this will be described by quantum field theory. Okay? And so that's a window, and we will be working in that window. Now, what happens if omega becomes comparable to J perp is quite interesting. It's a very interesting piece of physics there, because what you do there is you cross over from one-dimensional physics to three-dimensional physics. Because when your frequency, when your scale is small compared to J perp, you have really a three-dimensional magnet. In particular, you might order. Yeah? So it might spontaneously break the symmetry, you might get Goldstone modes. Yeah? So this regime of frequency is the regime where you cross over from one-dimensional to three-dimensional behavior. Yeah? And the resulting physics is very different to 1D, very different to 3D, and very, very interesting. But this is difficult to describe, and this problem is known as dimensional crossover. And so that's an area where people are still actively researching at the moment. So I think at this point I'll stop, because this is the end of my introduction to magnets, quite general. What I'll do in the next lecture and then in the following, we actually will now look at some models and try to solve them. But so this was basically to establish some context. If you have any questions, you can ask now, otherwise we have the break. Yeah?
When you say omega is too close to J, you You can't associate this with quantum field theory to the problem?
No, so the problem is, it's a good question. So the question was, when my scale at which I probe the system is comparable to J, can I still describe it by a quantum field theory? So the answer is no, because J is actually the scale at which lattice effects are inherently visible. Yeah? And the field theory will basically apply to a regime where you consider large distances. Large distances means low energies. Low energy compared to the lattice scale. Yeah? So you always have to be sure that you're in the right window. So it breaks down here, for sure. There was another question. Yeah.
You talked about the quasi-long range order in one dimension.
Yes.
What are the analogies with quasi-long range order in two dimension when you have BKT transition?
Yeah, okay, this is a good question. So the analogy is very, very close. Yeah, it's the same idea. Yeah? So essentially, rather than long range order, what you have is you have these power law correlations, which is the best thing you can have. And BKT in two dimensions, that's a classical theory in two dimensions, which maps actually quantum theory in one dimension. So from that point of view, formally, it's identical. Yeah? And we'll come to, I mean, the BKT physics, the physics of this Kosterlitz-Saris transition is one of the topics I hope to discuss on the example of the Heisenberg chain. Yeah. Okay, I think then no more questions, then let's have a break. And so we'll continue in 10 minutes.